we have a couple of slides haven't finished last week, but we have already explained in this week's tutorial. For your reference, I will still record this part. And as I explained in the tutorial, so there are three stages in liquid phase sintering. The first one is a particle rearrangement, followed by the solution reprecipitation, and the last one is a skeleton sintering. So let's say the first stage, the particle rearrangement. So as I said, the most important thing in liquid phase sintering is this large capillary forces, which has been used to pull the particle in as fast as they can. Okay, because of this, so this process will allow about even 100% densification at the very beginning. So you can see from this curve, it's a very fast rate. Okay, so the second stage we call it's a solution reprecipitation. So as we can see here, please first of all, please delete this one as I did not explain the equations. Dissolution of atoms at the contact point and reprecipitate away from the contact point. So what does this mean? So we can borrow this graph from the solid state sintering. Still remember, right? So the only difference between the solid state sintering and the liquid state sintering is just the media difference. Okay, so you can imagine the solid one, which means everything is happen at the vapor. Okay, outside is vapor, but if it's liquid, so it is the atmosphere is liquid. Okay, so you can see before here the atom is moved through where? Atom is moved through the vapor, but now the atom is actually moved through the liquid to move from the contact point. So contact point actually is just a green boundary. Okay, because the atom first, the atoms just touch to the other atoms at green boundaries, then move away from this contact area to where? To neck. Okay, so by doing so, you will have shrinkage and densification. So there's only one difference here you have to pay attention, which is the diffusivity difference in the liquid and in the vapor form. Okay, because as I said, in the solid state phase sintering, actually it happens in the vapor, it's a gas form, and in the liquid phase, actually it happens. All the migration of the atoms happen in the liquid phase. The diffusivity in the liquid is orders of magnitude higher than that in the solid state phase sintering. So which means what? You can imagine, as I said in the tutorial, you can imagine milk powder. Milk powder is moving much faster in liquid, am I right? Compared with in the air. So this is the difference. Okay, so make sure so your solid can move inside the liquid. Okay. So otherwise, okay, what is sintering? Sintering is all about movement of the atoms from somewhere to the other place, right? So in order for movement to happen faster, you have to make sure the diffusivity is also faster. So the last step is the solid state sintering. Okay, so once a rigid skeleton is formed, so liquid is not there anymore, so the solid state is going to. By summarizing what we have learned so far, in order for a very fast densification, please make sure these four conditions have to be met, right? The first one, obviously, is you have to make sure the state is less than 90 degrees, which is wetting, okay? So this is the first one. The second one is appreciable solubility of solid in liquid to transfer the materials. So you need a solid which can move through the liquid in order for the sintering to happen. So I take example, for example, again, milk powder. So milk powder can dissolve in water, so which means it can move through the water, but milk powder may not move through the oil. So if you put oil there, so you cannot make sure the atoms can move around. Okay, so that's the thing about solubility. So make sure there's enough appreciable solubilities of solids in the liquid to transfer the materials. The third one is quite self-evident, right? You need to make sure you have enough liquid. Otherwise, maybe some portion is still solid phase sintering, the other portion is liquid phase sintering. So please make sure there's enough one. So the last one is I did not explain the equation. So please remember, if you want higher capillary force, make sure you have a smaller particles, smaller requires a finer solid phase. But as we said, liquid phase sintering is good in terms of speed. It is very fast. It is much more rapid than the solid state sintering, and which means it will be much cheaper. But the problem is you will always have some glassy films at the grain boundary, so this can be very, very harmful. So what does this mean? So as I said, because the impurities is more or less like a liquid phase 8, right? This we call it sintering 8 is again, it is impurities. So it will never go inside any grains. It will only stay at the grain boundary to be as a glassy grain boundary. Glassy means amorphous. So this amorphous grain boundary can be very harmful. So I give you two examples here. The first one is a creep resistance. So this creep resistance will be largely compromised by glassy phase. Why is so? Because this glassy phase at the grain boundary is going to soften when it's heating up. So if you want high creep resistance, please don't use liquid phase sintering. The other one is if you want very insulative ceramics, so also please don't use this liquid phase sintering. Why is so? Because this glassy phase grain boundary can be very conductive. Okay, so that is why in today's electronic ceramics, liquid phase is not very much preferred. If you go back, if you want a very high toughness, make sure you have a duplex microstructures, and one of the structure has very high aspect ratio. And if you want a high strength, so you need a small grain size, uniform, and make sure there's no pores, okay, which means no pores. High creep resistance, again, you need large grains and free of amorphous grain boundaries. So this was explained in the tutorial. Okay, so this one, the optical transparency. As you can see, if you want a very, very transparent materials, okay, so make sure it is pore free. So it's important. And also there's another requirement, which is grain size. The grain size can be either much smaller or much bigger than the wavelength of the light. Okay, so visible light, the wavelength is from 380 nanometer to 780 nanometer. Okay, so which means your grain size need to be either much smaller than 380 nanometer or much larger than the 780 nanometers. Okay, so in order to achieve very transparent ceramics. Okay, so the low dielectric loss, so make sure it's a small and uniform grain. Catalyst, okay, catalyst, you need very large surface area. Very large surface area means what? It is equals to very porous, okay, very porous structures. Remember this one, it is important. Some students ask me what is the duplex structure in order to enhance the toughness. Okay, so this one is a duplex, means you have two different type of morphology. Okay, like the rest is very uniform, have similar structures, but in this case you can say the remaining is still quite uniform, but there's a big bridge in between. So this big bridge in between is more or less like a, we call it a filament or like fibers. So this fiber has a very high aspect ratio. So what does aspect ratio mean? So let's say you have, okay, let's say this one is, this side is A, then the other side is B. So the A over B, if it's bigger, which means it have high aspect ratio. Okay, so obviously like if it's a sphere, so it's roughly everywhere is the same. So it's not high aspect ratio. So obviously, so if we call this morphology is 1, the rest morphology is 2. So the inside one, this one have much higher aspect ratio. Okay, it's more or less like more elongated. So there's a one direction which is much, much longer. Okay, so that is, we call it a duplex structure. And how can we produce such structure? So as we have already explained in the factors affecting the solid state sintering, we said if you start with the powders, starting powder have very different particle size. So which means in the end, you're going to have very different grain size growth. Okay, so if you start with very uniform, you end up with very uniform. You start with very ununiform, so in the end, you will get something which is non-uniform. I give you this as a last example. So you can see, so the first one, a nominal, and second one, and the third one. So all of them are a nominal, but you can see the first one, because it is a perfect single crystal, which means what? Which means it is a very large grain size, just only one grain, am I right? So, and also no pores. That's why it becomes very transparent. So if you have a polycrystalline, it's no longer single crystal anymore, and some of the grain boundaries is going to scatter a portion of the reflected light. So it's something like this. It's more or less like translucent. You can still see a little bit, but very little. The worst case is opaque one. You have a large pores and have a lot of grain boundaries. So all this is going to affect the optical transmission. So for the summary of the whole part of the liquid phase sintering, so number one is there's a large capillary force by wetting liquid. So this large capillary force is going to attract particles come closer, enhance the densification. And we also said there's a 3 stages. The first stage, particle rearrangement. The second one is solution re-precipitation. And the third one is skeleton sintering. And make sure you understand these 4 conditions if you want densification to happen very fast. Okay, and of course, as I said, the liquid phase sintering is very helpful in many ways, and it is very economic because it's faster and may require lower temperature. But if you don't want any glassy film at the grain boundary, so please don't choose this method. And the last one, we said the property is very much dependent on the microstructures. Okay, so that table summarized a lot of important applications.